So inside the DHT, we want the DHT server peers to help us route to the content we're looking for. So that's the purpose of content routing. So we want them to know what we are looking for because they can help us. But at the same time, as we want privacy, we don't want them to know what we're looking for, right? And so that's a bit of the challenge. How do we make sure that they can actually help us to get to the content we want without revealing them what we're looking for? So I'm just going to go through a couple of definitions that you're going to see again in the presentation. So the multi-hash in IPFS is basically when you have some content. In order to get the CID, you will first hash the content. So if you have an image, you just make it through a hash function. You're going to get a binary hash. And then from this multi-hash, you will add some prefix, and you will get a CID from there, which is the string you can see. And then a concept that is important for the double hashing. So why double hashing? It's because we hash the content twice. So we're going to hash this multi-hash once more to get another identifier. And so in the slide, in practice, it's you don't directly hash the CID itself, but it's just easier to write it in the slide and to write the long version. And also another important component is the provider records. So when you get to publish or to provide some content in IPFS, what you're going to do is you do not drag and drop your content and store it on IPFS. The content will stay on your machine, and you will just make a pointer and write it in the DHT. And so anyone will be able to find this pointer and discover that you stored the file. So the provider records are this pointer that map the CID, so the content identifier, to the peers that are hosting them. So in the case, it's also possible that multiple peers store the same content. And so if you look up for a CID in the DHT, you will get a list of the content provider, and you can then ask them to retrieve the content. So now, how does pinning content to the DHT work? So I don't say provide, because we're not putting the actual content in the DHT, we only put the provider record. So what we do is we have our CID, and for some reason we're gonna hash it because we need a flat name. And so we hash this CID, so that's how it works today. So there's already a second hash, which is gonna give us a binary string. And we're gonna look in the DHT for the closest location in the binary key space. So the usually DHTs are represented as a circle, as we've seen in the last presentation. But in the case of Cademlia, it's better represented as a binary tree because we're talking about XOR distances. And so here we're going to see, so the request is going to be iterative. So first I'm going to ask the closest peer, or just a peer I know, okay, can you get me closer to the place I'm looking for? And eventually I'm going to find the closest peer IDs to the content, or to the hash where I want to store my provider record. And then once the request has converged, I will simply ask these peers, okay, can you please store this pointer for me, so that anyone that is looking for this content can then in turn ask me for the content. So these peers are going to start a provider record, and then any clients that knows the CID can simply hash it and look up for where the content is stored in the DHT. And you only need to find one of the closest peers that is storing a provider record. And then this peer is going to give you the provider record, so it's going to tell you where the content is actually located. So now you have the peer ID of the content provider. You can directly request it over BitSwap. So that's how content routing currently works. And so what does the DHT learn for each request? So for each request, the DHT learns if we take a DHT server peer that is going to help you to route your request, it will learn, of course, your peer ID because you open a connection with them, so they will know you. They also know your IP address. And as you request them some content, because you want them to help you, they will be able to associate your content with this peer ID. And so it means that they can track which CID you're accessing. But if they want to know really what you're accessing, they can just take this CID and in turn also request it to the DHT and get the same file as you. So anyone that wants to spy on you can just listen to your request, help you route them, and then resolve the same content as you, and you're absolutely tracked. So for instance, if the orange node here is malicious and the client asks them for the CID, then this node now knows the CID, right? And so it can in turn request for the provider record, learn where the content is stored, and retrieve the content, which is undesirable, and that's what we're trying to address with this upgrade. So why double hashing? How did we get there? So in IPFS, the way it works now is the content is addressed by the content identifier, but it would be great to have another identifier that would be specific for the DHT so that you can look up for some content in the DHT, and so the peers could learn about this file identifier, but then they cannot use it to request the content because when, for instance, you request the content over bit swap, it's going to be a different identifier, right? So we want to have different content identifier according to the different content routing mechanism or data transfer, so that we cannot link them together. And also what we want is that this new identifier shouldn't be hard to derive. So once we have the CID, we want to be able to efficiently find the identifier in the DHT. So that's one first improvement. So that if I request a key in the DHT, the node there can learn it, but cannot get anything from it. Now, in order to gain key anonymity and plausible deniability, what we can do is instead of requesting exactly for so this new identifier can be the hash of the CID, or you can hash the CID along with a constant, and so that will be the DHT identifier, so the second hash. And so in this case, in order to gain key anonymity and plausible deniability, because that's usually desired component of privacy, what we can do is request the hash of, request the prefix of this second hash, which means that in this case, we can request a prefix and we will get approximately in the right region in the tree. So the node can still help us route to the right place. But as we request the hash, they will, the prefix, there will be probably many provider records that match this prefix. And so we will get multiple provider records, so that the DHT server node that are serving us this provider record don't know exactly which content we're looking for. So I say, okay, I'm looking for approximately this content. Again, I get many provider record, and I can only select the one I'm interested in and discard the rest. However, this gives us key anonymity, but no LDAR diversity or T-closeness, which means that if, let's say in a specific branch of the tree, for a specific prefix, there is one file that is very popular and everyone wants to access it, and let's say 10 other files that nobody wants to access it, then if somebody makes a request in this specific branch of the tree, then it's very likely that they access the popular content. So it's not perfect, but at least it gives us a plausible deniability. And so, yeah, we can still do correlations attack on the prefixes, so the branches. One other component that we can use to improve our system further is we can encrypt the provider record. So now so the provider record are these pointers that I put to the DHT to indicate that I store the content, and my peer ID is in the clear, which means that anyone that hears about the request, even if it's a different hash, can know that I am storing the content. They won't be able to request me the content because they only know the DHT identifier, so I will know that they don't have the CID and I will not give them. But my peer ID is in the clear, so as a writer, a content provider, I can be associated with this content. So what we can do to address it is we can encrypt the peer ID with the CID itself. And this can be done through symmetric encryption. And so it would guarantee, so anyone can still request this new DHT identifier and get the provider record, but now only the peers that know the CID, so like the CID would be the secret to be able to decrypt this provider record, only the peers knowing the CID will be able to decrypt it and know that I am storing the file. And now, so this has the encryption has some undesirable effects, which means that now if I know the content of some file, I can say that somebody else is providing it, and I can create a provider record pointing to somebody else to DOS them. And so the DHT server cannot verify anymore if the peer ID in the provider record matches my peer ID because I'm uploading it. So what we can do is we can simply sign the encrypted provider record so that the DHT server can verify if so the signature of the encrypted provider record that the server cannot read matches my connection with him. And so in turn, it's also good because the client, so when a client then gets the encrypted provider record along with the signature, they can decrypt the provider record to get the decrypted peer ID, and they can verify the signature against this peer ID. So that's roughly the specs, so what will change. So we will have the encrypted peer ID that we encrypt using the CID. We will have the signature of this encrypted peer ID. And so the new provider record will be a mapping from the new DHT identifier, so the hash of CID, to the encrypted peer ID. And we also want the signature to be there. So that's the easy version, but in practice, we're gonna encrypt with the multi-hash, which is contained inside the CID, and we'll hash with a constant string in order to avoid collision. So now, how will the system work? So I will still look up, so for the second hash of my content in the DHT, and I will store, so it will not be exactly the same location because the salt will be different, but the process will be exactly the same. So I'll look for the closest peer. And now I have my encrypted peer ID. So I encrypt my peer ID with the CID. I sign it, and I send it to those peers in the DHT. And then the clients that want to look up some content is going to look up the hash of the CID and even a prefix of it, so that the nodes don't learn a lot about the content that I access. And then what I'm gonna get is I'm gonna get a bunch of provider record. So that's a system parameter that we can adjust. So in the K anonymity, we can choose the K, of course. So here, I'm gonna get like 4 different encrypted provider record, and I'm gonna discard all the one I'm not interested in, because I'm interested only in a single one. I'll be able to decrypt it because I know the CID. And once I decrypt it, I can verify the signature because it was signed with the private key of the peer ID that is storing the content, right? And so then I have the guarantee that the peer ID that I have at least knows the CID. a malicious node could not have created valid encryption with using the CID as a key. And I can get my content from there. So now, what privacy guarantee does it bring? So it brings us key anonymity and plausible deniability, as the DHT will serve us multiple provider records. So if we say that the DHT is an entity, they cannot determine exactly which content I am accessing. So my peer ID could be associated directly with the CID I was looking for, and now it can only be associated with the hash of the CID. So it means that if the adversary already knows the content I am looking for, they can still know what I'm accessing. So if we take an example, there's a decentralized kind of YouTube platform, IPFS, and we have a global adversary that is going to crawl it and index all of the videos. They can in turn compute the hashes of all of the CID. And so when I make a request with this identifier, they already have it, so they can still track my request. But in the case where I upload or I advertise my holiday pictures on IPFS and I want to share it with my friends, nobody knows the CIDs except with the person that I share the link with. And so nobody can actually know the data that is being accessed. Also, so we get some writer privacy improvement because the provider record is encrypted, so it's not in the clear. We don't know anymore who is storing specific content. However, the DHT server will still know the content provider because you have to open a direct connection with them. So they still know, but the rest of the DHT doesn't know. And now let's go to the overhead. So the overhead is quite low, I would say, because so there is no, let's say, RTT or additional hop in the routing. Routing works exactly the same. No additional packet when doing the lookup. It's just when we retrieve the provider record, we will retrieve K, so K anonymity instead of 1. So that's like so the number of bytes on the network will increase. On the storage side, so the DHT server node need to store provider record, and those provider record will be larger because they will now contain a signature in addition to the peer ID. And there's also a computation overhead because a signature has to be produced for each provider record, and the provider record have to be republished over time every 24 hours, which means that every 24 hours you need to produce a new signature for each piece of content that you are providing. So now the changes that it would imply for like the IPFS environment. So only libp2p has to be upgraded. So I mean, when I say only, it's like Go libp2p, Rust libp2p, Nim libp2p, JS libp2p. So all DHT implementation have to be upgraded. But then the application building on top of libp2p or IPFS would automatically benefit from this. As an application builder, you don't need to change anything. This change integrates in IPFS reframe. So there's a pull request where we specify the new private content request. And the double hatching approach will also be implemented by the indexer. So yeah, this approach would be for the DHT and the indexer with the same interface. And so Elizabeth from ChainSafe, that I couldn't make it today, is currently working on the implementation. So yeah, you can check if you're interested.